In this video, we are going to be looking at congruent triangles and proving different theorems about quadrilaterals based on those congruent triangles. The problems come from lesson 7.2.1. In earlier chapters, you studied the relationships between sides and angles of a triangle and solved problems involving congruent and similar triangles. Now you are going to expand your study of shapes to quadrilaterals, and we're going to focus on what triangles can tell us about parallelograms and other special quadrilaterals. Before we get too in-depth with these quadrilaterals, it's helpful to revisit the definitions just so we're all on the same page. Today we're going to be focusing on two types of quadrilaterals, which are a closed four-sided polygon. We are first going to be looking at parallelograms, which is defined to be a quadrilateral with two pairs of parallel sides. And then we're going to look at, briefly, just a kite, and that is a quadrilateral with two distinct pairs of consecutive congruent sides. But first, we'll look at the quadrilaterals. And it wouldn't be a CPM problem if we didn't have someone who was thinking about parallelograms and wondering if there are as many special properties for them as they are for triangles. Carla remembers that it's possible to create a shape that looks like a parallelogram by taking this triangle, tracing it, and rotating it. So it says to trace this triangle and rotate it. I've already done that for you here in red. And you can see that the markings carried over as well. The question is this shape truly a parallelogram? Well, by definition of a parallelogram, that would be two pairs of parallel sides. So I guess the question is, do I know that opposite sides have to be parallel? Well, if you think about our converse lesson yesterday, parallel sides come from having alternate interior angles that are congruent. And I can see these lines have alternate interior angles that are congruent, therefore these lines must be parallel. Looking at my sides on the left and the right, again, I have a different pair of alternate interior angles that are congruent there, created by this transversal. So then these lines would also be parallel, because when I know alternate interior angles are congruent, lines are parallel. That is the converse of the alternate interior angles theorem that we proved way back, I think it was like chapter 2, or maybe chapter 3, that we looked at that. Because I have two pairs of parallel lines, yes, I know this must be a parallelogram. So the basis of most of chapter 7 boils down to this. We are going to take a look at different triangles and look at what we can prove from triangles. And then once I know the triangles are congruent, I'm going to have a whole bunch of other facts that I can prove to be true. So we're curious, does this work for all parallelograms? That is, does the diagonal always split the shape into two congruent triangles? So we're going to look at this and say, can I prove these two triangles are congruent? So we're going to start this process by making a flowchart to show the triangles are congruent. We will start with the definition of a parallelogram because that's what this shape is. And it might seem strange starting our flowchart this way, but truly all I know is that ABCD is a parallelogram. That's what's given. From there, I'm going to use the definition of a parallelogram to say that I have two pairs of parallel lines. So I've added in here that AB is parallel to CD, and then again, that's because it is a parallelogram, and that AD is parallel to BC. Now, as you're filling in your flowcharts, as you're doing this with me, if you need to pause the video, that is a great strategy to help you get the details filled in. Now I need to look and see what these parallel lines actually give me. If I draw my first set of parallel lines, I always like to extend them here. And then I draw my transversal in a little thicker. I can see that these angles right here would be alternate interior angles. Because the lines are parallel, I know that those angles must be congruent. So I would know angle ABD is congruent to angle CDB. And again, that would be because those are alternate interior angles. Now I'm going to look at the second set of parallel lines, the left side and the right side. as I extend those parallel lines and draw those, that transversal, I see a new pair of alternate interior angles right here. So off of AD is parallel to BC, I'm going to write angle ADB is congruent to angle CBD. Again, those are alternate interior angles. And now I have two pairs of angles congruent, so I'm really just looking for one more piece of information, and I see it here in this side. That is a shared side, and I know from triangle 1, DB is congruent to triangle, or side BD in the second triangle, in triangle 2. Again, anytime a side is congruent to itself, we call it the reflexive property. And I listed this DB and BD because if I look at triangle 1 here, DB goes from the red angle to the black angle that I have marked with those arcs. And in triangle 2, the red angle to the black angle is BD. So this needs to be switched around here in this case because of the symmetry of the shape. From there, I'm able to move on. I have my angle, an angle, and a side. Looking at my picture, my side is between those two angles. So I'm able to take those and prove that triangle ABD is congruent to triangle CDB. And that reason, again, is angle-side angle congruence. So it looks like the question that we were asking earlier is, does this work for all parallelograms? That is, does the diagonal always split the shape into two congruent triangles? Is yes. It always works. I always have two congruent triangles, and I proved it to be true by angle-side angle. Now, where I'm going to apply this is to take a look at the properties of this parallelogram. As soon as I know these triangles are congruent, I know all of their corresponding parts are congruent. So that means that AB corresponds to CD. So those sides must be congruent. So I can list this at the bottom of my flowchart. Congruent triangles yields congruent parts. That also works for this pair of sides on the left and the right. Again, because the triangles are congruent, those corresponding parts must be congruent. But I can also see something happening with the angles here. I see angle A congruent to angle C because those are also corresponding parts. Again, my reason is congruent triangles yields congruent parts. So these congruent triangles are able to tell me quite a bit about the properties of a parallelogram, and we will continue to discover different theorems, but for right now, I know that opposite sides have to be congruent because the triangles are congruent, but also opposite angles have to be congruent because the triangles are congruent. We will record these properties at the end of the video. Now, if you remember, we started this by taking two triangles and rotating them to make a parallelogram. Our friend Kip here is confused. He actually just reflected his. So he took this first triangle here and flipped it across this line with the second triangle there. The shape he made is a kite, because if this is my original, when I do my rigid transformation for my reflection, I have two pairs of consecutive congruent sides. His transformation that he used was just a reflection. And then my question is, what do congruent triangles tell you about the angles of this shape? Well, if I look at the angles of the kite, I see that one pair is the same. And I see that the other angles looks like they got cut in half. Again, these are properties that we're going to keep track of at the end of this video. And we're going to do one more investigation on a kite here. Kip shared his findings about his kite with his teammate Carla, who wants to learn more about the diagonals. So she quickly sketched this one, and we're going to add on it here. We're going to add the other diagonal of this shape. Then we're going to consider how the diagonals may be related. Okay, I think it looks like they meet at a 90-degree angle here. I also think that it looks like this one maybe gets cut in half. I'm not sure though. Okay, if you've not already done so, write a conjecture. So my conjecture would be that the diagonals are perpendicular and that one of the diagonals gets cut in half. So now we're tasked to prove it. It says, when she drew the second diagonal, Carla noticed that 4 new triangles appeared. If any of these triangles are congruent, then they may be able to help us prove the conjecture from part B, she says. Examine the triangles below. Are they congruent? If so, create a flowchart proof like the one from 750 to justify your conclusion. Well, I think I have side angle side here, so I'm going to set about to prove it this way. My first step is to write what's given in the diagram. AC is congruent to BC. The next piece of information that I need to record is the fact that angle ACD is congruent to angle BCD, and again, that's given to me in the diagram. And then finally, I'm going to share about CD being congruent to itself because of the reflexive property. And then that gives me all the information that I need to say triangle ACD is congruent to triangle BCD. Now, my original conjecture was to show that the diagonals were perpendicular, so to show a 90-degree angle, and to show that the one diagonal was cut in half. Well, since I know these triangles are congruent, I know all of their corresponding parts must be congruent. That means AD must, in fact, be congruent to BD. And I know that is true because congruent triangles yield congruent parts. The second piece of information that I know is I know that angle CDA is congruent to angle CDB. And I also know that that is true because congruent triangles yield congruent parts. Now, if I want to say that they're 90 degrees, I need to include a couple other facts that actually have nothing to do with the triangles. And that's the fact that those two angles together make a straight angle pair. I know that they equal 180 degrees because they are a straight angle pair. If I know that they equal 180 degrees together, and I know that they are the same, then I can say, putting these two pieces of information together, that they both have to equal 90 degrees. And that would just be by doing a substitution. If they're congruent, they have the same measure. So I could swap out this one for that one, and then I would have two of them. I can use some algebra skills to simplify that and say that each one is 90 degrees, which then allows me to say the diagonals are perpendicular. I can say CD is perpendicular to AB because they meet at a 90-degree angle. That is the definition of perpendicular. Okay, so it gets a little involved at the end, but I think it's easier to see where this comes from my congruent triangles, and then I have my diagonal that gets bisected, but then I have congruent angles here that have to add up to 180, so each one is 90, meaning those diagonals are also perpendicular. Okay, so let's take a minute and let's record these properties. We're going to be studying these for quite a bit, so we want to make sure that we get the information right and record it in a safe spot where we can keep it handy. So I went ahead and filled in the definition. A parallelogram is a quadrilateral with two pairs of parallel sides. And now let's add the properties that we've proven. We've proven that opposite sides are congruent and also that opposite angles are congruent. Let's look at a kite. A kite is a quadrilateral with two distinct pairs of consecutive congruent sides. We know that one pair of opposite angles are congruent. We know that the diagonals are perpendicular. And we also proved that one diagonal is cut in half or is bisected by the other diagonal. Go ahead and keep this handy. We will come back to this and fill this in throughout the rest of the unit. Thanks for watching.